Okay, once more, up to reach. Where were we at? Well, we're just about to find the spaces we need to talk about the Beers embedding. We have our space of Beltrami differentials, which is the uniform and infinity of the G invariants, which elements are infinity H, so that's those mu's in N infinity H, which are in the unit ball, and our G invariant. So we have these guys. Then we have our Teichmüller space, which is defined as equivalence classes of these people here. So if S is the upper half plane quotient by its recovering transformations G, we have Teichmüller space. T of S. So T of S is some nasty set. As we said, it's defined as an equivalence class of these things, and in the previous talk, equivalence classes can be anything. So we have some projection from here up to here. And then we have also defined the space of holomorphic quadratic differentials on our surface S, or equivalently holomorphic functions on the lower half plane, which is G invariant. So we can view that as phi's from the lower half plane to C, so that they're G invariants this way. This relationship means that they project two holomorphic quadratic differentials on the surface, G and G. And we also want them to have finite hyperbolic supremum law. Where the rho is the hyperbolic density. So I put axes on these things to indicate that these are sort of linear finite spaces, but not on here. And we defined a map in terms of Schwarzian derivatives. Let's call it slightly S. From, well, it takes a Beltrami differential and it produces a holomorphic quadratic differential. And script S or mu is the Schwarzian derivative of F. Lower mu restricted to the lower half plane and then its Schwarzian derivative. So we defined what this was last time. We said that, well, we start with an element in here. So this is just one of these. We extend it to be defined on the whole plane by extending it to the lower half plane to 0. We solve the Beltrami differential equation, get a QC map F lower mu. This guy happens to be conformal on the lower half plane, so we can take the Schwarzian derivative. And this is a 1-1 map from here onto here. So we get S going from up there to down there. And then this induces the Beers embedding.
You said that's 1-to-1? That's 1-to-1 on Teichmüller space.
So it's 1-to-1 onto its image. Yeah, so the induced map you get here is 1-to-1 onto its image. What do I call that? Capital phi. So this capital phi here is the Beers embedding and 1-to-1 onto its image. Now, the image here is contained in a ball of radius 6, and it contains a ball of radius. What we can do now is find a section for the Schwarzian derivative map, or the Alfors-Weil section, which is defined in here. So we can find a section which goes back up here. Let's call it sigma. So this is the alpha file. So for brevity, I hope you believe me that you can define this thing and it has the properties that we want. So if you come up with sigma and then come back down by a Schwarzian derivative map, you get the identity.
Can you pick another color?
Blue not working?
No, green.
No.
I didn't see green. Where did it go?
There is green. It's close on your left.
That's it. Green.
How's this? Any better?
Good.
Okay, no. So the inverse, well, the Apples-Wild section here, the image of that up here will project to something in Teichmüller space. And it will contain the base point. So we get what we get here is an open set in Teichmüller space which contains a neighborhood of the base point. Okay. So we found the neighborhood of the base point that we constructed in this way, but what we really want to do is construct neighborhoods, open neighborhoods of all the other points in Teichmüller space. And we can do that in the following way. So suppose we start with a mu, which is a G-invariant Beltrami differential, then the quasi-conformal map F upper mu, we've said this before, conjugates G, or the surface, no, it conjugates G onto another covering group, G upper mu. So that, well, we can project F mu to be a quasi-conformal map from S to S1. Okay, then there's a map. Alpha sub mu from, get this the right way around, BHG to Beltrami differentials with respect to the new group we've got, G upper mu. And you can define it the following way. So F upper alpha mu of nu is defined to be the inverse of F upper mu, then composed with F upper nu. So almost not important what it is, but what it is in isometry. For the respective Teichmüller metrics, and it induces a map tau mu from T of I'll put S1 in there, S1 CS given by G being sent to the class of G composed with F inverse.
Alastair,
Yes.
do you mean the Teichmüller metric there, or because you're on the
Right. So this induces anisometry for the Teichmüller metrics given by this. That's why. So thank you. So what this tells us is we want to have this picture here, but translated over here by this mapping here, tau mu. In fact, tau mu is called the translation map. So we have tau mu going that direction. That points there the base point of T of S1, which gets mapped to, let's see if purple works. The base point over here is being mapped by this translation map here to the class of mu. So then we can play the same game that we played here. We have a corresponding Schwarzian derivative map which goes from here down to here. We induce a Bers embedding again from Teichmüller space here into a bound open set in this space of quadratic differentials. And again we can find a section that comes back up like this. So let's draw the same picture in. So this open set here is being sent by the Uppels-Wahl section up to some set up here, which is then projected back down to some open neighborhood of the base point in T of S1, and then we bring that over here by this translation map, T of mu, and we get to cover a little open neighborhood of mu with this open set here. And let's call this open set V sub mu. And let's call the mapping which sends this down to here, I haven't the colour, I'll use it, by H sub u. So H sub u is just doing the inverse of the translation map, which is the projection, and then coming down by the Bers embedding, which is also one-to-one onto its image. So this is projection from here to here.
Just defined on that neighborhood mu. So that's TLS.
This H mu, yeah, is just defined on the pink bit there. So what have we got? Well, we have that the collection of V mu's form an open cover of our Teichmüller space TS, and it turns out that the collection of pairs V nu, comma H nu forms, well, defines a complex structure on Teichmüller space T of S, with respect to which the Bers embedding is holomorphic and in fact bi-holomorphic. Okay, so there's a theorem there, there's things that need to be proved, of course, which I'm not doing. All I'm doing is hopefully giving you an idea of how you can start with Teichmüller space and model it as a complex manifold on all these various Q spaces here, these Q of L G U's that you get. One other thing I'll just say about the Beers embedding is that we get that it's biholomorphic, but it's only locally by Lipschitz. So we have Teichmüller space here, and it's being mapped onto something here by the Beers embedding. And if you go towards the boundary here, then points which are not very far apart in the Q metric that you get here will get far apart when you go back under the Beers embedding and look at their distance with respect to the Teichmüller metric up here. Okay. I'm just going to leave that there for 1 second to digest. Are there any questions about what's going on here? Stunned silence.
So you really just need one of these charts to get the complex structure that says that these particular coordinate changes are complex anyway.
Right, I mean, this is a global holomorphic chart from here onto here. Okay. So as I just said, since the Beers embedding phi defines a global holomorphic chart, so Teichmüller space tangent space can be identified with QLG, the tangent space out of the base point. So base point here getting mapped to 0 down here in QLG. So since we have a holomorphic embedding here to here, tangent space can be identified with this. Now if we take any other point, so mu here, then we have map from here over here, going across by the translation map, then down here by the Beers embedding, so that we can view this Banach space here as the tangent space to Teichmüller space at the point nu. So the tangents bundle over Teichmüller space is a collection of all these guys. So what about the cotangent space? Well, it's the Bergman space. Let's call this A1 LG. I think I briefly mentioned it last time. So I guess the A is because this definition involves an area integral, or it's absolutely integrable. It's a space of holomorphic quadratic differentials, well, holomorphic functions on the lower half plane which satisfy the G invariance for being a quadratic differential. And so that's the integral over omega, where omega is a fundamental domain for, let's call it L. L quotiented by G. We want that to be finite. Okay. So having this definition means you project onto the surface to a holomorphic quadratic differential on the surface whose L1 norm is finite. And fun fact, every linear functional on A1 of LG can be written as L of phi is the integral over our fundamental region omega. The hyperbolic density is to the power minus 2, psi bar phi, for some psi in Q of LG. So what we can do is pair up elements of A1 and Q in this way. Every linear functional can be associated with some element of Q, so it turns out that the dual space of A1 is Q. I really want to wrap this up.
So this says that A1 is sort of a pre-cotangent space, right?
Right. So S is of finite type, so that means genus G and n punctures. Then the complex dimension of this Bergen space is 3G minus 3 plus n. So in particular, it's finite, which means that if we take its dual, that can be identified with the space we started with. So this means, in this case, that we can identify A1 and Q. So they're actually the same space. And when we allow G or n to be infinite, this is no longer true. And I don't think you even have that A1 has to be contained in Q. You can have elements of A1 which aren't Q. But you still have the important duality that the dual of A1 can be identified with Q. I guess I'll talk about it tomorrow, but there's a subspace of Q called Q0, which is the pre-dual space of this space A1, and the dual of Q0 is A1, the dual of A1 is Q. In finite dimensional case, they all coincide. Not for infinite type though. Okay, so the theme that can probably be explored more tomorrow is that describing various properties of the Bergen spaces A1 should tell you something about time on the spaces. So if you know some properties of how two Bergman spaces behave if they're related. That might tell you something about the space Q, which might then tell you something about the Teichmüller spaces. Okay. That, as I say, will be left for tomorrow. Probably. Now, if we pretend I haven't rubbed off this picture, we had our Beltrami differentials up here, we had them being projected to Teichmüller space, and then we went down to the space of quadratic differentials with the pairs embedding, and everything with the structure we described is nicely holomorphic. So if you have a path which approaches zero, a differentiable path which approaches zero in the space of Beltrami differentials, then that is going to come down to a differentiable path down here in the space of quadratic differentials approaching zero, and then you can lift this back up to here by the alphas file section and get a differentiable path. If you start with one down here, you can get one up here which can be chosen to go through zero. So the point is each Beltrami differential mu represents a tangent vector. Let's have that in infinity hg. Represents a tangent vector at the base point of Teichmüller space. And of course, more than one Beltrami differential can represent a particular tangent vector in Teichmüller space. So a single tangent vector can be represented by many Beltrami differentials. So in fact, we can, quite apart from the Teichmüller class of Beltrami differentials, have a class of Beltrami differentials which determine the same tangent vector. So we can define the equivalence class mu tan, so that nu is in mu tan if mu and nu represent the same tangent vector. Okay, in the interest of brevity, I'm kind of going to gloss over this fairly quickly, but I will just say that the equivalence class mu tan you can write as mu plus ng, where n is a linear subspace of your space of Beltrami differentials. Which annihilate everything in the corresponding Bergman space. Okay, so we have two equivalence classes of Beltrami differentials. One, the Teichmüller equivalence class, is some highly nonlinear equivalence relation, not so easy to tell when two elements agree. But we also have this tangent class of Beltrami differentials, which it's easier to tell when they agree because we have this linear subspace of element infinity that tells us how this equivalence class looks. Now we'll come back to this mu tan in our chapter that we're about to start now on extremals and geodesics. So in Teichmüller space there is a close relationship between geodesics and extremal quasi-conformal maps. So if we've got a mu, which is a Beltrami differential, then we call it extremal if for every nu in our Teichmüller equivalence class of mu, we have that its subnorm is bigger than the subnorm of mu. So mu realizes the smallest distortion that we have in our Teichmüller class. And observe every class contains an extremal by a compactness argument and we also say it's uniquely extremal if we have a strict inequality here. So if the infimum is realized by one and only one Beltrami differential. So if we recall the Grech argument that we had back in lecture 1, that was to do with quasi-conformal mapping from one rectangle to another, which sent the vertices to the vertices respectively. And we said that the smallest dilatation quasi-conformal map that you can have that does this from here to here is just a stretch. So it's extremal, and it turns out that it's also uniquely extremal. So, for example, the affine stretch between rectangles is uniquely extremal for this problem. Okay, and this basic idea of having an affine stretch being uniquely extremal crops up again when you try and talk about unique extremality of elements in various Teichmüller classes. And there is a similar notion for the tangent class of Beltrami differentials. So mu is extremal for mu tan if the optic sting subnorm of mu is less than or equal to subnorm of nu. For all nu in Teichmüller class of mu. And the obvious notion of unique extremality applies as well. So what would be great is that you always are in this situation. You could always find the uniquely extremal map in the class that you're interested in looking at. And I'll say Teichmüller's theorem in a minute, which will tell us that that very often happens, but there are examples where it doesn't. And the example that Strabel gave is called Strabel's chimney. So what this is the union of the lower half plane with a cylinder here, and on the x-axis that's between x equals 0 and x equals 1, and then it goes up like this. And Strabel showed that f of x plus iy equals x plus iky for k bigger than 1 is not uniquely, is extremal for its boundary values. So this just means you're stretching up in that direction and you're stretching down in that direction. And he showed that if you start with any other quasi-conformal map which agrees with f on the boundary of the chimney here, its distortion is going to be at least k. But okay, you can replace f with something which also has the same distortion. Let's call it f0, which agrees with f in, well, chimney, and is the identity elsewhere. Well, f restricted to the real axis intersecting the boundary is just the identity. So this map here has the same boundary values as f in this domain, but the distortion of this is exactly the same as the distortion of this. It's k. So f0 has the same distortion as f. So f is not uniquely extremal. I mean, it's even worse than this. It's not just that we've got two mappings which are extreme. Well, we can replace the identity by anything which stretches by a factor less than k in that direction. It'll still have the same boundary values. It'll still be extremal, and it's not going to agree with f. So in this case, we have infinitely many extremal mappings. Suppose we start with an extremal mapping. Well, it turns out that T mu is extremal for a class of T mu as t runs between 0 and 1. And it's an exercise to show that this path that sends t to the class T mu is a geodesic for the Teichmüller metric in Teichmüller space. So what this tells us is that every time you have an extremal, you can produce a geodesic from the base point to that point in the Teichmüller space, and the geodesic looks like this. So this tells us Teichmüller space is path connected and contractible. So when I drew that picture here, representing Teichmüller space as something that, in the space of quadratic differentials, that looked like this, this wasn't too far away from an accurate picture, in that it's contractible and we can shrink it down to one point, and there aren't any holes. And in fact, when the dimension of our Teichmüller space is finite, our Teichmüller space is homeomorphic to a unit ball in the corresponding dimension. So when G and N are finite, T of S is homeomorphic to the unit ball in R of 6G minus 6, I guess, plus 2N.
Yeah, I mean, so you're, even in the case of infinite type, you're saying it's contractible?
Yep.
But I don't, I mean, since you don't have uniqueness of geodesics,
Okay, you
I'm
have
not
uniqueness
sure.
of geodesics on an open dense set. Is that enough? Maybe you have to do something different to prove contractibility in the infinite
Okay.
dimension.
I think you need the ideal extension. You need some equivariant extension.
Right.
And then you can, but you need to produce the mu in a natural way.
Right, the Slokowski time.
So what's the conclusion?
It is true in
They're saying
the
it's true,
statement.
but that's not the proof.
Oh, this doesn't prove it for infinite time. No.
Okay, good.
No,
But it is true that it's contracted.
That's what
Put that sentence there. Okay. We're going to talk about, in the remaining couple of minutes, and I might just stop till you stop me. I might just keep going till you stop me. If we let you, sorry, not you, we want phi to be a holomorphic quadratic differential, which is L1 integral with respect to our the L1 norm. Then we call mu equals k mod phi over phi for k between 0 and 1, maybe I even want just k to be this. Well, we call this object a Beltrami differential of Teichmüller type. So this has constant complex dilatation, and it turns out nice things follow from Beltrami differentials of Teichmüller type. And let's just also note that we define the corresponding QC map F upper mu that is said to be of Teichmüller type. Sorry, it's the Teichmüller map. Excuse me. Okay. So then Teichmüller's theorem which he stated and more or less proved, says that if we have two closed surfaces, S and S1, and F from S to S1 is a quasi-conformal map, then the Teichmüller class of F contains a Teichmüller map, and moreover, a Teichmüller map is uniquely extremal, or it is uniquely extremal. I would say boundary values, but these surfaces don't have boundaries. So this says that when your genus is finite, then every Teichmüller class contains a uniquely extremal map, so you have a unique geodesic between any two points in the Teichmüller space. So this basically deals with the finite dimensional case, and then it's a question, how much do the conclusions of Teichmüller's theorem hold when you go to infinite type surface theorem? Teichmüller's theorem, just a good start. Let me just say one or two words about how this works, and sort of how it is similar to the rectangle stretching that we had. So, if our I'll try to be differential of Teichmüller type, so the one we get here, if it's like this, then phi is a quadratic differential on S, and we can talk about trajectories and so on of this quadratic differential. But if we choose a natural parameter, or if we choose a regular point, let's call it Z or S, then in these coordinates, phi just looks like dz squared, and mu just looks like, well, if the function we're getting from the phi, the function part here is 1, then we've got 1 divided by 1, so mu is just a little k. And the solutions f upper mu in the plane with mu's that look like this are affine maps. So the examples we were talking about with straight chimney over there, where you're stretching, they have complex dilatations that look like constant, and similarly, if you have a constant complex dilatation, that's just corresponds, or can just correspond to some affine stretch. So then if psi is the push forward of phi by our quasi-conformal map that we've got here, F u, and if we choose appropriate coordinates on our image surface x1 related to the quadratic differential psi, then in these coordinates, psi looks like let's say ku plus iv. So in other words, what we can do is, on our surface, we choose coordinates based on our quadratic differential phi, and we get coordinates that look like this. And then when we hit this by our Teichmüller map f mu, well, what's happening is that these are getting stretched in a particular direction. So it's exactly the same kind of thing that was going on with the rectangle, except now we're doing it in local coordinates on the surface. You're just stretching in a particular direction. And this works whenever we have closed surfaces. We get a Teichmüller type arbitrary differential, a corresponding Teichmüller map, and we get this picture.
So this doesn't mean that the map is pseudo-anosov, right?
There you go.
This doesn't mean that the map is pseudo-anosov or something like that.
Don't think so, I'm not 100% sure. Okay, maybe in the next few minutes, I'll just present some results on what you can do when you go to infinite type surfaces. Okay. Well, the Reichs-Strabel inequality is a key tool. So let me just say it's a key tool, and if you're interested, then you can look up afterwards what it says and how it can be applied. But it says that if mu is a Teichmüller, is in the base point of Teichmüller space, then the L1 norm of phi is less than or equal to the integral over omega 1 plus mu phi over mod phi, that all squared, divided by 1 minus mu squared, the absolute value of phi. So an application of the Reichs-Strabel inequality tells us that Teichmüller type maps are uniquely extremal when we have them. So this extends Teichmüller type maps being good to infinite type surfaces. I guess the key point here is that in the definition of Teichmüller type maps, we need that our corresponding phi is L1 integrable, so this thing is finite. And that need not happen. If we do have a Teichmüller type map, it's good, they're uniquely extremal. Okay, when do we have Teichmüller type maps? Well, the frame mapping condition tells us when okay, so I'll write this down. So let S be of infinite type. And let's consider a point in our Teichmüller space want to denote by K0 the dilatation of an extremal F naught in F. Okay, so then if there is a compact set C contained in our surface and a QC map F1 contained in our Teichmüller equivalence class, so that well, we want to look at the distortion of our mapping F1, but off this compact set, so away towards the ends. Subnorm, if that is strictly less than K0, then our equivalence class contains a Teichmüller type map. So if you come up with an equivalence class, and in that equivalence class you can find a quasi-conformal map so that the distortion of that map outside a compact set is actually smaller than the distortion of the map taken as a whole, or the extremal map taken as a whole, then it turns out that our class contains a Teichmüller type map. And if we have these conditions satisfied, the point of Teichmüller space we have is called a Strabel point. So Strabel points are good. They're points where we have a Teichmüller type map, and that map is uniquely extremal, and it tells us there's a unique geodesic connecting the base point to that point. And results of Lakich and with L and G say that the set of Strabel points is open and dense in Teichmüller space. Okay, just as an example with these Strabel points, the base point is not a Strabel point, so the base point contains a conformal map in its class, and the distortion of a conformal map is 1. So when we take any quasi-conformal map and we look at its distortion of some compact set, it's always going to be at least 1. So this is not a strict inequality, and the base point is not a Strabel point. On the other hand, set of Strabel points are open and dense in Teichmüller space, but the set of points that aren't Strabel points form a perfect set, so there are Strabel points. But there are points which are not Strabel points. Okay, let me just finish up with some results on that.
Connected.
Are you still assuming that your infinite type surfaces are,
I'm allowing to either have genus G or finite number of punctures, so I'm not having.
you could have an infinite number of punctures?
Yeah.
Okay,
Yeah.
but that's the restriction, because that is a restriction, right? The Fuchsian group is of the first kind then.
Right. Yeah.
All right, that's just,
We're not quite sure if you can remove that restriction off the top of my head, but I'm being safe.
but for that.
What about the connectedness of Strabel points?
Sorry?
What about the connectedness of this set of travel points.
What about the connectors? They must presumably be connected because imagine the geodesic you get when you join one point to a stable point will go through other stable points, I think. Right, so if you have some stable point which has some Teichmüller map that looks like that, then I guess if you just multiply by some number between 0 and 1, then this is still a Teichmüller type. Okay, generalized Teichmüller type are of the form K mod phi over phi, where now phi, or the integral over mod phi, may be infinite. So, an example of this would be the infinite strip and just stretch it. This, the corresponding quadratic differential for this is just the identity of 1 dz squared, and that integrates to give infinity. So sometimes these are uniquely extremal. Sometimes not. Not helpful. There are conditions which tell you when a generalized Teichmüller type map is unique. One of those is uniquely extremal. Those in Lakish, Markovich, and Matejevich settled lots of questions to do with uniquely extremal mappings. One thing they did do is that a generalized Teichmüller type mapping is uniquely extremal if and only if you can find a sequence of holomorphic quadratic differentials which are integrable, so that phi n converges to phi A1G uniformly on compact subsets, or locally uniformly, and 2 K, the one norm of phi n minus the real part of the integral of omega phi n, that is mu, goes to 0 as n tends to infinity. So these sequences here are called Hamilton sequences. There's a lot more you can say about them in relation to extremal maps. But if you can find a Hamilton sequence like this, then you get a uniquely extremal generalized Teichmüller type mapping. But there are examples, I don't think are particularly nice, where you have a generalized Teichmüller type mapping and it's not uniquely extremal. Okay. So Li Zhang has a couple of papers on geodesics and Teichmüller space, and that's just one result. So if S is an infinite type, then you can find 2 points, nu and nu, in Teichmüller space with infinitely many geodesics connecting them. So these aren't going to be of Teichmüller type because they're not extremal, you don't get geodesics. And he has various other pathological properties of the metric geometry of Teichmüller space under the Teichmüller metric when you have surfaces of infinite time. So you would love there to be every quasi-conformal class to have Teichmüller type mappings so you can include the lovely things you have in the finite type case. You don't get that. You only get on an open dense set, you get nice Teichmüller type mappings which give you unique extremality and give you unique geodesics connecting 2 points in Teichmüller space. You have examples where things go wrong. Okay, on that downbeat note, I'll call it a day.
Yeah, so for the straight bullet chimney, you had actually, you sort of, you know, can interpolate between any two of the geodesics by, you know, you can move, you have one parameter families of geodesics connecting the 2 points. Right.
Between points which...
Well, I don't know, you have families of maps. I'm wondering, I mean, is it always true that if you have two different extremal maps for the same points, can you find a family that goes
connect them in the same family?
Yeah.
Or I don't know, I mean, Teichmüller equivalence is a nasty equivalence relation, so how would you go about that? I mean, you can't just sort of take a mu in your space, your Beltrami differential space, take a nu and then draw a line between them or anything like that. There's no reason that should maintain you in the same Teichmüller class. Because, I mean, so Teichmüller space was defined as sort of normalized quasi-symmetric maps, and I don't see how you can say anything about the quasi-symmetric map just looking at your Beltrami differential. Maybe you can.
In that case, how many of these main geodesics are there here? Is it comfortable? Or?
I believe so. I think you can sort of parameterize it with some interval. Okay, so just fire it in a different direction. So, yeah. I mean, in these papers, there's an explicit construction of constructing a mu and a nu geodesics, and I think there are ways you can get.
Other questions? Thank you again, Alastair.